안녕하세요. It's great to be back in Korea. This is my third time in this country, and we're hoping that this is going to be an annual event, bringing our team to Korea. I wanted to start with some history, and artificial intelligence is not new. What we consider as the beginning of artificial intelligence is a workshop that happened at Dartmouth College in 1956, where they hold up 10 white men inside a room and have them talk about the future of the world with artificial intelligence. And even back in 1956, they were predicting that in a few years' time, artificial intelligence will take over. And of course, it did not happen. What we consider now as the start of the modern age of artificial intelligence is 2022, because there were so many events that happened during that year. Starting off with April of 2022, when OpenAI released DALL-E 2, which is a software that would create images from text prompts using a technology known as latent diffusion. And this technology became available to the community in September of 2022. In July of that year, DeepMind announced that its AI tool called AlphaFold has been able to predict the protein structure of every known genomic sequence of protein. And what's more important is that they share the protein structures to the rest of the world by making it available at the European Molecular Biology Laboratory. And these protein structures were accessed by investigators and researchers who are doing research in medicine as well as biological sciences. July of 2022, Stability AI and CompVis released Stable Diffusion. It's a similar technology of creating an image based on text. And this was released as an open source project, complete with a code repository and checkpoint files. But pretty soon, critics became aware of some of the dangers of this type of technology. They said that this could create alternative histories. It could create political disinformation. It could even create child sexual abuse materials. In the same month, August 2022, a Colorado resident named Jason Allen won a digital arts photography competition. And when he won it, he said that he used artificial intelligence to create this painting, and the people flipped out. November 2022, Meta announced that its AI called Cicero was able to beat human competitors in an online strategy game called Diplomacy. Diplomacy is a complex game to participate in because it requires persuasion and negotiation and collaboration. And none of the human competitors were aware that they were fighting or they were competing against an artificial intelligence bot. Truly, we had passed the Turing test. But the biggest event of that year was the release of ChatGPT, which is a large language model based on GPT 3.5, I believe. And within 5 days, the CEO of ChatGPT announced that this chatbot was able to reach 1 million users. And this is unprecedented. We've never seen technology being adopted this quickly. And within 2 months, ChatGPT reached 100 million users. And since then, we have seen large language models performing task after task. It had passed every examination known to woman and man. And in healthcare, we found that it could even guess the correct diagnosis of very complicated cases. Summer of 2023 is the beginning of the end. We saw all the data conglomerates really joining forces and concentrating the power of artificial intelligence within a few hotspots. In the United States, we saw the partnership between Microsoft, OpenAI, and Epic, which is the biggest electronic health record system in the United States. And since then, we have seen large language models being available to not just patients, but also to clinicians. We have never seen grifting at this scale. People are peddling AI left and right. Every advertisement has that two letters, AI. And overnight, we saw the crypto cowboys turning into AI cowboys. And pretty soon, every other LinkedIn profile is saying that they are AI experts. So what's so different about artificial intelligence? I will give you three key crucial differences between AI and previous technologies that we have seen. The first is that AI is boundless when it comes to applications. It is really poised to upend every human task that involves thinking. And for that reason, AI is going to be very difficult to regulate. The second difference is that this technology advances at such a rapid speed. And for that reason, I keep saying, and I will repeat this later again, that there will be no experts in AI. We have to count on community intelligence. We have to count on collective wisdom. We need to start teaching each other and learning from each other. But we see a lot of technologies that we don't understand, and yet we use them without any problems. As a clinician, I don't really understand how MRI works, but I have no problem prescribing or ordering an MRI for my patients in the intensive care unit. Most of us here do not understand how GPS works, but our lives are dependent on GPS. The difference is that these technologies are quite narrow in application. And for that reason, we could sleep at night thinking that some organization did its job and made sure that these technologies are safe to use. But the biggest difference between AI and other types of technology is the way we develop artificial intelligence. One of the key messages that I want you to take home is this: artificial intelligence is inequitable by design. And why is that? The raw materials for artificial intelligence are the data exhaust of systems that we know are discriminatory. So if all we're doing is dumping gobs and gobs of data into an encoder or transformer, then we risk cementing all the problems that we see in our legacy systems. A month ago, in the United States, they passed a law saying that health systems and healthcare providers are going to be held accountable if they are proven to use an artificial intelligence tool that is discriminatory. And we think that this is throwing us under the bus because we are not trained to be able to distinguish what is good artificial intelligence tool and what is not. And soon after, the lawyers are rejoicing because this is a gold mine for lawyers. They are now prepping to be litigating health systems and providers who might be discriminating against their patients using artificial intelligence. The next few slides are not meant to scare you, but I'm sorry, they will. I'm going to go through some algorithms that have been deployed, that have been evaluated, and I will tell you what are some of the pitfalls and dangers of these algorithms. The first one is not really a machine learning-based algorithm. It is an algorithm that is supposed to predict which patients who are admitted to the hospital will develop acute kidney injury. Although this is not machine learning-based, the task is similar to what we are designing artificial intelligence for. So what they did in this study is to prospectively evaluate an algorithm that will inform the clinician if their patient is about to develop acute kidney injury. And of course, this is a very welcome tool for us because sometimes we are buried in data and we just don't see that our patient might be at risk for developing acute kidney injury, which means that we have to do some different measures to make sure that we mitigate this risk. When the investigators were applying for ethics committee approval, this is what they showed them. This is what the alert would look like. And it's very simple. It's just saying that based on the creatinine, the serum creatinine of the patient, based on some other criteria, we predict that this patient will go into full-blown acute kidney injury. And when the ethics committee was deciding whether this is a high-risk or low-risk intervention, they all deemed that this is low risk because they are not introducing a new intervention. It is just informing clinicians of the likelihood that a patient will develop kidney injury. It is not meant to replace their decision-making, but they thought that this is additional information that they could find valuable. So what were the main findings of this study? They looked at a composite outcome of either death, admission to the intensive care unit, or requirement for a dialysis during that hospitalization. And they had this algorithm deployed in 6 hospitals. 2 are large academic centers and 2 are small community hospitals. What they found is that the effect of artificial intelligence varied depending on which hospital. Overall, they did not find any effect of providing this algorithm to the clinicians. There was no improvement. There was no drop in the death rate. There was no drop in the admission to the ICU. There was no drop in the likelihood of getting dialysis for kidney failure. But what was very disturbing is that in the 2 small hospitals, the death rate doubled. And they cannot explain why giving this artificial intelligence harmed some patients. So looking back, this algorithm was not low risk at all, because if it were low risk, it shouldn't have killed more patients after deployment. But the main message here is that a clinical decision support tool, even if it's not replacing clinical decision, can harm patients. More and more artificial intelligence tools are becoming available for us clinicians in the United States. And a lot of these tools are not considered healthcare related because these are tools just to help us with administrative tasks. So there have been a lot of tools that are offering to summarize the patient notes so that we don't have to read pages and pages of what happened to the patient. But even these tools that are meant to just summarize notes are not risk-free. And in several papers, they have shown that although majority of the summaries are quite accurate, a lot of them contain small errors that could have detrimental downstream effects. In this paper, they tried to use artificial intelligence to draft letters to patients, draft letters to other physicians. And similar to the summarization task, they were finding that it was adding some statements that could be potentially harmful to patient. One that comes to mind that was seen in some of these letter drafting tools is one that was deployed in a cancer clinic. So these are letters that were being written by cancer doctors to their patients to summarize what happened during the visit. And what they found is that the artificial intelligence was recommending the patient to lose some weight, because most letters coming from doctors are always advising patients to lose weight because it's better for diabetes, it's better for heart disease. But you will never advise a patient with cancer, you will never advise a patient with an eating disorder to lose weight. The message here is that data is very context dependent. And when we train large language models, we do not tell large language models what this content was made for. We just input that into this training computer to see and understand which words belong together. And that's how large language models are developed. They do not really understand. They're just looking at co-occurrence of words to come up with sentences. The peddlers of AI are saying that AI is going to make the lives of doctors and nurses easier. It's going to make radiologists faster in the way they're reading X-rays, it's going to improve their performance. Once again, that assumption is wrong. This is a study that was published earlier in the year looking at the impact of an artificial intelligence tool provided to radiologists who are reading X-rays, CAT scans, MRIs. And once again, they found that the effect of AI on different radiologists is different, it's diverse. And the more alarming thing is that we couldn't predict how the radiologists would behave when given an AI co-pilot. What they found is that the poorest performing radiologists, they did not improve universally. Some got better, some did not get better, some actually got worse. And they found too that some well-performing radiologists, they started making mistakes as soon as the reading of the AI is different from theirs. They start losing confidence. This is the problem when you're developing AI in a laboratory or in a company. We have to develop AI human systems because we cannot predict how the humans, how the users will behave once they are working together with artificial intelligence. This paper came from our group, and it's one of the most concerning discovery that we've had regarding large language models. For this particular study, what we did was we asked GPT-4 to give us differential diagnosis, possible diagnosis, when we describe a certain patient. We were also asking GPT-4 what should be the workup, what should be the test, what should we give the patient if this patient were to be seen in the emergency department. And for this project, we used case vignettes that we got from the New England Journal of Medicine. So they have been used for educational purposes before. But what we did was each time we were putting this text prompt, we were changing the sex and the race ethnicity of the patient. So same description, but one time we will say it's a white woman or a black man or a Hispanic man. But the description of the case is exactly the same. And let me just go back to the results of the study. So when we gave the study the case of someone who has shortness of breath, and that case is one of pulmonary embolus, there's a blood clot in the lung. Every time we say that the patient is a woman, GPT-4 would include anxiety disorder, panic attack, as one of the differential diagnoses. But we do not see this if the patient were a man. When we gave GPT-4 the case of a college student with sore throat, everyone gets a diagnosis of strep throat, except if the patient were black and male. It starts suggesting that this could be gonorrhea or syphilis or some sexually transmitted infection. So as you could see, it learns very easily some of the stereotypes of society. In the United States, it learned that blacks are more likely to be malingering when they come to the emergency room. They're just looking for narcotics. And this is not the right way to make clinical decision making. You have to base your decisions on clinical features and not based on your stereotypes. The more concerning thing is when we were asking GPT-4, what should we do for this patient presenting to the emergency department? Once again, we were giving it the same case, but we were changing the sex and the race ethnicity of the patient. We found that across the board, if the patient were black, GPT-4 is less likely to recommend a CT scan, an MRI, or recommend consultation with a specialist. Once again, it's ignoring the symptoms of black patients. At present, this is the way that developers or large language models are making sure that their products are not biased. It's called reinforcement learning from human feedback. And all they do here is they give the large language model to a group of users to stress test the large language model. And they're making sure that it will not give overtly racist, overtly sexist, overtly ableist recommendations. And who are these people who are providing the reinforcement learning from human feedback? These are workers in Nigeria, in the Philippines, in Brazil, who are paid $1 a month to look for these overtly racist, sexist, ableist input and output from large language models. And I would argue that most of the biases that exist in large language models are not overt. They are very difficult to detect. And I really am skeptical that people in Nigeria, Colombia, Philippines, Brazil would be able to tell you if the response of a large language model is discriminatory or not. So trying to do what we call fine-tuning when the model is already developed, which is the reinforcement learning from human feedback, this is similar to raising your kid to be racist, to be sexist, to be ableist, to be discriminatory. And once the kid is grown up, you tell the kid, oh, you have to attend some cultural sensitivity training. It's not gonna work. You have trained your kid to have these stereotypes, to be biased. And then suddenly you would like your kid, when the kid is grown up, to not reflect these biases in the way they make decisions. So far, I've only talked about the biases of large language models. Biases in numeric data is even more difficult to detect. This is a list that is by no means comprehensive. These are some of the data issues that we have discovered that could have profound distal effects on clinical machine learning. I'm only going to focus on the first and the fourth because of time. So the first one is bias from medical device. Unknown to almost every one of us, every medical device that we use in the hospital and clinic is biased. And that's because the way we develop them is typically with some healthy subjects. In the United States, the biggest and most notorious example of a biased medical device is the pulse oximeter. So this is a device that approximates the amount of oxygen in your bloodstream by using infrared technology. And what we have been discovering for the last 2 decades actually is that it doesn't work well if you have a dark skin tone. It over-predicts the amount of oxygen in your bloodstream. And we have papers that we have published showing that we have harmed dark-skinned individuals. We did not give them oxygen when they should have received oxygen because we were fooled by a medical device that doesn't work well for them. And last summer, we published this summary of medical devices that we have, that we use in the intensive care unit that does not work for all the patients in the intensive care unit. Apart from harming the patient, it also becomes a real problem when we start building machine learning models and artificial intelligence. The other problem that I have in my list of sources of data bias is about sampling selection bias. So sampling selection answers the question of who made it to the database. We are very critical of machine learning courses that do not teach the students how to interrogate how the database came about. Who made it to the database, who did not make it to the database. Because if you don't understand this, you will not know when bias is encrypted in your algorithms. This is a study that I keep presenting to illustrate the problem with sampling selection. This study was published in the midst of the pandemic. It's looking at the predictors of death when a patient with COVID pneumonia presented to the hospital. The data came from the Veterans Administration. Veterans are those who served in the military previously and have since retired. And that already gives you really the reality that they do not represent the US population. This is the main table of that study. On the first third of the table, you could see the effect of increasing age as regards the likelihood of death if the patient is admitted for COVID pneumonia. And It's not surprising to see that as the age increases, the hazards ratio of death also increases. So again, we know this. We observed this during the pandemic. The older you are, the more likely you're gonna die. But if you look at the middle third of this table, it tells you that patients who never smoked are at the highest risk of death from COVID pneumonia. And the lowest third of this table is showing you that patients who have normal body mass index are also at highest risk of death. And for those of you who were at the front lines of care during the pandemic, we know that this is wrong. We know that patients who smoked before are more likely to have a greater damage in their lungs. We also know that we saw more patients who are overweight, who were admitted to the intensive care unit and who eventually died from COVID. So what happened here? Why was this finding discovered in this particular cohort? The reason is sampling selection bias. Among the veterans, among previous military personnel, there are more smokers than non-smokers. And if you are a non-smoker and you develop COVID, you are unlikely to be admitted into the hospital. So there, the hospitalized cohort is no longer representative of the cohort coming from the population. The same is true with obesity. If you are a veteran, or even if you're not a veteran, if you are not obese, it's less likely that you will develop a severe enough COVID that will warrant admission to the hospital. Once again, there's a sampling selection bias. And for that reason, we discover these spurious associations. They're spurious associations because they're not true. They're an offshoot of sampling selection bias. So our group is renowned for offering the Medical Information Mart for Intensive Care database to the rest of the world. And it's a database that has more than 70,000 users, and it's produced close to 10,000 citations in Google Scholar. We asked ourselves, is there sampling selection bias with MIMIC? And there is. In the United States, what we found is that if you're a Black or Hispanic patient and you develop cardiac arrest outside of the hospital, you are less likely to be resuscitated. That means that if you're Hispanic or Black or Native American and you develop cardiac arrest, you're less likely to reach the intensive care unit because you will die at the scene. And that means that these underrepresented patients who are in MIMIC are probably very different from the underrepresented patients who did not make it to the intensive care unit. And this creates sampling selection that will lead to spurious associations that will be encrypted in algorithms. In 2013, a gentleman named Robert, I forgot his last name, McAdams, I believe. He lived in the south side of Chicago. He received an unexpected visit from the police commander of the Chicago Police Department. And he was told that he should not commit future violent crimes. And the warning caught him by surprise because he has never been arrested. He has never had any encounter with law enforcement. But it turns out that his name appeared in a hit list of 400 individuals in the Chicago Police Department of people who are likely to commit violent crimes. And the algorithm was proprietary. We do not know how it was making those predictions. And since it's proprietary, it cannot be interrogated for errors or bias. This type of algorithm is now being used by police departments, not just in the United States, but also across Europe. And it's very dangerous because we know that they're very biased. It turns out that artificial intelligence is not very good when the ground truth is debatable and when reasonable people like us could debate what is the correct answer or not. Despite that, companies are still saying that they could predict the future. HireVue is a company that offers a software that is supposed to predict job performance of applicants based on their answers to a few questions, such as, is your desk messy? It sounds to me like horoscope, but this algorithm decides the fate of millions of job applicants every month. In the United States, there's another software that is supposed to predict if a high school student who is applying for college will drop out of college before finishing it. Once again, the algorithm is proprietary. We do not know how biased it is. We do not know what features it's using to make that prediction. And in healthcare, there's a company called Appriss, which has come to dominate state prescription databases. They offer this AI product called NarxCare. And NarxCare is supposed to give a prediction of how likely a patient will be addicted to narcotics. So in some states, they require doctors and nurse practitioners and pharmacists to run this algorithm before they prescribe or dispense opioids. And you can imagine how biased this algorithm is going to be. Another paper that came from our group was a serendipitous discovery. We were not expecting to actually find that artificial intelligence finds features that are invisible to the human eye. In this study, which was published 2 years ago now, we found that it was trivial for artificial intelligence to guess the race ethnicity of a patient based on the X-ray without any other information. And we were able to validate this in X-rays coming from different institutions from different countries. We were also able to replicate this finding in other types of imaging modalities, CAT scans, MRIs. They seem to know what is the race ethnicity of the patient. But the most perplexing thing is we couldn't figure out what it was learning. The first guess, of course, is the disease distribution. Maybe all the chest X-rays from black patients had pneumonia, and all the chest X-rays from white people did not have pneumonia. Wrong, that wasn't the answer. We trained the algorithm just on images with pneumonia, and it could still tell us whether the image belongs to a black patient or a white patient. It wasn't the age. Maybe all the white patients are older, and you could infer the age just by looking at the bones on chest X-ray. It wasn't that either. It wasn't even a specific anatomic portion of the X-ray. At one point, we were feeding the algorithm random crops, sometimes from the shoulder, sometimes from the heart, sometimes from the lungs, and it could still tell if the patient is black or white. Our hypothesis is that it has something to do with the technology that was optimized for a certain demographic. So every few years, this equipment would require recalibration. They take what we call phantom images, and typically it's white college-age males who are recruited to get the phantom X-rays, and then they recalibrate the technology so that it's best in terms of the image based on this particular demographic. And as soon as the patient is not a white college-age male, it starts detecting some noise. From our friends in ophthalmology, we learned that artificial intelligence can tell you if the picture of the back of the eye belongs to a man or a woman. Our ophthalmologists are astounded because they themselves cannot tell you if this fundus photo belongs to a man or a woman. Last year, this was published actually 2 years ago, and they showed that artificial intelligence can tell if you're rich or poor. But this one we thought was cheating a little bit because it used all chest X-rays, and we think that it was basing its prediction on the number of findings on the chest X-ray. So our group repeated this study using normal chest X-rays without any findings, and it could still tell patients who are on private insurance versus those with public insurance, Medicare and Medicaid. And it's learning from small bits and pieces from the X-ray whether this person is rich or poor. Why do we care if computers can identify race, ethnicity, sex, or socioeconomic status from datasets based on features that we cannot see? That brings me to the story of Clever Hans. I'm hoping that some of you have heard about the story of this horse. Clever Hans was an Arab stallion. In 1900, he was bought by this retired German schoolmaster named Wilhelm von Osten. And during his retirement, he was bored, so he started teaching the horse how to identify numbers and how to perform simple calculations like addition, subtraction, multiplication, and even square root. Like, I can't even do square roots. But he was surprised to see that Clever Hans knew the answers. He took the horse on road shows, but later on they discovered that the horse was not even performing the calculation. It was sensing the heartbeat of the people around him. Every time William von Osten points to the correct answer, and of course the audience could also multiply and add, they also know the correct answer, they start getting excited. And Clever Hans could detect the change in heartbeat. And it neighs, and everyone thinks that the horse knew the answer, but it did not. As soon as they blinded William von Osten as well as the audience as to the question, Clever Hans wasn't clever. It couldn't get any of the answers right. Are there Clever Hans in the machine learning community? There's lots of them. We call them now the Clever Hans phenomenon or shortcut features. In this famous study from two investigators, one from University of Washington and the other one from UC Irvine, they trained an algorithm to distinguish wolves from huskies based on photographs. But all the pictures of the wolves had snow in the background, and none of the huskies were photographed with snows. And not surprisingly, the algorithm learned that. It started saying that every time it sees snow, it would guess that it's a wolf and not a husky. This will happen too if algorithms can tell if you're man or a woman, if you're straight or gay, if you're Catholic or Muslim, if you're rich or poor. They will start using those features to make predictions and classifications. After all, we are training algorithms based on human data, and as humans, we know that we have implicit subjective biases. So imagine this. Some of you might already have this app on your phone. It's an app that you can use to take a photo of a suspicious mole, and it will tell you the likelihood whether it's cancerous or not. But during training, it was using primarily photos of light-skinned individuals. And more importantly, it learned that images that are taken by expensive iPhones are less likely to be cancerous compared to those that are taken by cheaper Android phones. And it starts using that feature to make a prediction. You can imagine how much medical errors will be made and how misdiagnosis will occur at scale. So I did not mean to scare you, but I hope that you are, because there are so many things that we need to do to be able to leverage the power and the value of artificial intelligence. Two things need to happen very, very quickly. The first is we need to educate everyone, and we need to make sure that everyone has some basic understanding of artificial intelligence, and more importantly, what are the risks associated with its use. The problem is, how do you teach a technology that is moving so fast? I mentioned earlier, and I'm gonna say it again, there will be no experts in artificial intelligence. We can only have collective wisdom. We have to teach each other, we have to learn from each other, we have to watch each other's backs, because no organization can regulate artificial intelligence. Everyone has to step up and has to do its job. This is the ethos of Datathons, and I hope some of you are attending the Datathon tomorrow and Sunday. In Datathons, we bring in people with different backgrounds, with different expertise, with different perspectives, with different lived experiences. And everyone has something to teach each other, everyone has something to learn from one another. We cannot teach artificial intelligence in a classroom full of computer science students, and in another classroom full of medical students, in another classroom full of pharmacy students. We need to bring them together in one classroom. They have to start teaching each other because this technology is moving so fast. The only way I could keep up is through WhatsApp. And I talk to students there, and the students come from different countries, different backgrounds. They share papers, they give their opinions and their perspectives about the papers. This is the classroom of the future. It's not gonna be at the universities or in high schools. It has to be education without walls, where everyone is truly participating in both the teaching and the learning. So we have been organizing datathons for 10 years now. The very first one was in 2014. Last year, we organized one at MIT, and this time we reached out to community colleges and inner city high school students. We are against having these datathons and hackathons only involving the top universities, because the people who are studying at top universities are very privileged, and they may not really understand the problems that are provided by the burden of disease. It's very important to work with people who truly live the problems with the diseases, and this is why we need to bring them with us in our journey. We have rich networks in all parts of the world, and our strategy is to connect the dots. So we have been doing datathons in Central and South America, and we introduce them to each other because everyone wants the same thing. Everyone wants to leverage artificial intelligence in order to improve the way we deliver care, the way we educate, the way we regulate. So I think it's a waste of energy if each one is doing their own thing because there's so much to learn from each other. So that's what we do when we go to South America. We're going to Colombia next month, and our partners from Mexico, from Chile, from Brazil, from Argentina are all gonna be there, and they're gonna be exchanging notes, they're gonna be brainstorming together. And we have rich networks in Asia as well. We will be in China in September, in Singapore in December. And more recently, we have been partnering with professional societies. So these are the societies of cardiologists, societies of critical care medicine, societies of nephrologists, because they're grappling with how do we teach current generation and the next generation of clinicians, because they do not have enough clinicians who understand this, and there will never be enough clinicians who understand AI who can teach this to the learners. We need to bring in our computer science colleagues, we need to bring in our colleagues from the social sciences and allow them to truly leverage each other's expertise, perspectives, and lived experiences. More recently, we have been organizing what we call Health AI Systems Thinking for Equity, or HACE policy camps. We're having one tonight, so I'm hoping that I will see a lot of you. And what do we do during these events? We form teams, and each team has to be composed of people with different backgrounds, and we give each team one algorithm to dissect. We were in Africa, for example, in Uganda last February, and one of the teams was assigned an algorithm that could predict, based on a headshot, whether the person is straight or gay. What they did was they trained the algorithms on photos from dating sites in the United States, that's Tinder and Grindr. So there's a label of whether the photo is that of a straight male or a gay male, a straight woman or a gay woman. And not surprisingly, the algorithm was very accurate. And then we asked the students, imagine the worst scenarios if this algorithm gets into the hands of bad actors. And the students were really scared because in Uganda, homosexuality is a crime and you could be put into jail for being homosexual. So just imagine if this algorithm is used by the government and wanted to use this to prosecute someone. This is my final message that I would like you to take home from this talk. Ultimately, the impact of artificial intelligence hinges on who gets to develop and who gets to design artificial intelligence, who gets to distribute it, and who it gets distributed to. And most importantly, who gets to control, who gets to regulate, who gets to set the agenda and sit at the table. This is a meeting that was convened by President Joe Biden, and the purpose of the meeting is to form committees that will make sure that artificial intelligence is safe. And who got invited to this meeting? It's the CEO of OpenAI, the CEO of Anthropic, the CEO of Microsoft, the CEO of Google, a lot of industry actors. And I don't know about you, but I don't trust industry to keep the public safe. We've heard this saying before: every system is perfectly designed to achieve exactly the results that it gets. The medical knowledge system now, as we have it, is perfectly designed to produce health disparities. And the way we are creating artificial intelligence now is perfectly designed to cement the health inequalities that we're seeing in our systems. Last year, I found this YouTube video that I thought was very interesting because it imparts 3 important messages. In the video, there's a basketball game that's going on between 2 men's teams. And in the middle of the game, they managed to entangle the net. So they interrupted the game, and each of the men started to try to jump to disentangle the net. And no one can do it. So they had to cancel the game, and the men left the court. And within 1 minute, the women's cheerleading squad walked into the court, formed a pyramid, and disentangled the net. There are 3 messages from the video. The first is that competition typically kills collaboration, and you need collaboration to solve complex problems. All the men were trying to out-jump each other, showing the rest that they are the best person to solve the problem. In artificial intelligence, we keep hearing, our data is bigger than yours, our models are deeper than yours. That mindset is not going to advance artificial intelligence to inch us closer to the world that we want. The second message is that you cannot solve problems if you surround yourselves with people who think like you. You need a diversity of expertise, of perspectives, and lived experiences to truly see the problem from different lenses. And finally, the biggest message of all is that problems cannot be solved by the same people who created the problem and who are preserving the problems. So the solutions to the healthcare problems that we are discussing now cannot come from us privileged people, because we have continued to preserve these problems. It will have to come from people who truly understand the issues, and that means that we need to bring in other actors to have a seat at the table. We need to bring in the patients, and we need to bring in their caregivers. And with that, I'm happy to answer any questions from the audience. Thank you.